In this video, we are going to continue the discussion of finding radiation from an electric dipole, an oscillating electric dipole. So what we came up with now is some approximations for these distances of, so r plus and minus, basically the distances of the charge to the point in space where we're measuring v, and where we left off now is how are we going to handle the cosine right here. And so what we can do is we can now add in our approximations for r plus and r minus. And so this would now be cosine of omega times t minus omega over c times r times 1 minus plus d over 2r cosine theta. So let me make sure I close all my brackets. Okay, so let me combine some terms. So I get cosine of omega t minus r over c, which is essentially, the origin time, the time at which the radiation started, plus or minus omega d over c cosine theta. So the r's canceled, so this r and this r cancel each other, and we're left with this term right here. Okay, so now what I can do is I can break this up into, since I have a plus and a minus, it's basically, thinking of this as the cosine of phi1 plus or minus the cosine of phi2. And so you can go back and look at your trig identities, and what you'll find is that you have cosine of omega t minus r over c times the cosine of omega d over c cosine theta. So we got this kind of weird function of a cosine inside of a cosine, minus plus sine omega t minus r over c times the sine of omega d over c cosine theta. Okay, so let's make another approximation. So this would be approximation number 2. So the first approximation was that d was much, much smaller than r. In this approximation, d is much, much smaller than c over omega, which, what does that mean? Well, if the wavelength lambda times the frequency is equal to c, then lambda is c over f, which is c over omega over 2 pi, which is now 2 pi c over d. So what we're saying here is that d is much, much smaller than the wavelength of the radiation that we're going to produce. So if that is true, then if that's true, then we use small angle approximations, which would say that the sine of phi is equal to phi, and the cosine of phi is approximately 1. So if that is true, then what we get from here is that cosine omega dc cosine theta essentially drops out, and what we're left with is that the cosine of omega t minus r plus or minus over c is approximately the cosine of omega t minus r over c, and that other cosine is approximately 1, minus plus omega dc cosine theta. So that's the sine. The sine is approximately equal to the angle itself, times the sine of omega t minus r over c. Okay, good. So now we don't have to worry about any sines of cosines or cosines of cosines. We can now write it out in this way. Okay, so that means I can now write my electric potential as V as a function of r, theta, and t, now as the dipole moment times the cosine of the angle theta over 4 pi epsilon naught r minus omega c sine omega t minus r over c plus 1 over r cosine omega t minus r over c, and that's it. So basically I multiplied out those two terms, and I got essentially put in the dipole moment term. If we look and see, does this really make sense? Well, let's say we don't actually oscillate the charges around. We just have it as a static dipole. So if it's a static dipole, that means that omega is equal to 0. So V r theta t is now equal to this right here, which gives me P0 cosine theta over 4 pi epsilon naught r squared, which is the case for a static dipole that we got from one of the earlier chapters in the book. That's good. So that means that what we've worked out here for the this time-dependent case, the time-dependent basically oscillating dipole moment actually can be reduced when you stop oscillating it to the original result. So that's good. That gives us a confidence that what we made is now a more general explanation as opposed to a very strict particular case. Okay. Okay, so now we're going to make a third approximation. So approximation number 3 says that the distance that we're measuring is much, much bigger than c over omega, which is essentially the wavelength. So what we're doing now is we're saying that we're going to be measuring, so if this is my dipole, which is now oscillating back and forth, which is now going to produce radiation, that the point out here in space, r, that we're going to be measuring the radiation, is much larger than the actual length of the wave. So we're many, 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 many wavelengths away from our oscillating dipole. So this right here is called the radiation zone. Okay, so that's the radiation zone. So when we do that, how does that help us in what we have here? If I can go back. In this equation right here, so how's that going to help us out, kind of clean this up? And so what it says is that so we said that r is much, much bigger than c over omega. So that is now going to clean up our sines and cosines. We can make an approximation with the sines and cosines. And what we're left with is essentially that 1 over, that this 1 over r is now going to go towards 0. We're very far away from the dipole, which means that we can now kind of eliminate that cosine term, and what we have is this. So, by making this approximation that we're very far away, that means that this term here goes to 0, which means this whole cosine term falls out, and what we're left with is just the sine. All we're left with is the sine term. Okay, so that cleans it up a little further. So to do this derivation, we've basically made 3 approximations. Which were that d is much, much less than r, that d is less than lambda, and that lambda is much, much less than r. Okay. Okay, so in doing so, we now have a form of the electric potential. Okay, so to work out the magnetic potential A, that's the next step. And once we have the magnetic potential, then we can solve for the electric field. So we can figure out what is the electric field now of this radiating dipole that we have. Now the derivation for finding A is going to be a little bit more involved, and so I'm going to push that off into the next video lecture.